Hi guys. I already made about half this video this morning and realized my microphone was off. It was muted. So here's round two because 2020 just can't get any better. All right, so let me try and focus in on this thing a little bit better. There we go. And I'm going to go over this thing in its entirety. So, if you get number 1 or number 6 or whatever, just forward fast through the feed until you get to the number that you're interested in seeing. I thought it would be nicer than, the Zoom videos at school. There's a delay of you like looking at my desk because I'm taking attendance, and then there's background noise and whatever. So I thought without any interruption, I would make the video on the review from home. So hopefully there will be no interruption like the dog barking or something like that. Okay, number 1, we're given a function f of x equals root x, okay? And in part A, we want to find the average rate of change on the interval from 9 to 9.1. Okay, so we're choosing a point a little bit to the right of 9, and we're going to compute the slope of the secant line, right, or the average velocity. And just remember that the average velocity is f of b minus f of a over b minus a. It's just the slope of a line, okay? It's the same as y sub 2 minus y sub 1 over x sub 2 minus x sub 1, okay? No different. So this is our a, this is our b. So our average rate of change is f of 9.1 minus f of 9 over 9.1 minus 9. Easy peasy. And now what we have to do is we have to compute these things right here and substitute them back into this formula. So to the side, f of 9.1 is just the square root of 9.1 because our function is root x. It's a simple function. And of course, f of 9 is the square root of 9, which is 3. So what you should do is just leave some weird number under the radical, okay, until you're ready to use your calculator to compute it. So we've got root 9.1 minus 3 over 0.1. And if we throw that into our calculator, we're going to get 0.166. Okay, so that's our average rate of change over this little interval right here, teeny tiny interval. And in B, you're asked to find the average rate of change from 8.9 to 9. Okay, so no biggie. You're going to do the same thing, right? You're going to have f of 9 minus f of 8.9 over 9 minus 8.9. And f of 9 was 3, and we don't know what f of 8.9 is, so we're just going to leave it under the radical over 0.1. And if we put that into our calculators, we get about 0.167. Now, I would go out more digits than I have here generally. That way I don't make a rounding error because AP will not give you points if you make a rounding error. Okay, you'll lose points. So you don't want to make a rounding error. But anyway, in part C, we want to estimate the instantaneous rate of change at x equals to 9. So, I have a 9 here as a right endpoint. I have a 9 here as a left endpoint. And I've got some values here that I computed for just this reason. So I'd say the instantaneous rate of change is about 0.166 plus 0.167 divided by 2. And we get 0.16. I think it was 0.167. Let's see if I still have it in my calculator from round 1 of the video. Yeah, 0.167. And you're done. Okay, so you can always do this with any little interval with a table for average and instantaneous velocity. Of course, this you're estimating it the best you can. In number 2, and you're going to have to. So on YouTube Live, if I look at my computer, my video is backwards. So when I move my paper to the right, the screen is moving it to the left and so forth. So you'll have to forgive me because I forget which way. And So I go in the wrong direction. In number 2, we've got a ball dropping from a height of 400 feet. So if you've got 400 feet here, you got a ball on the end of this stick, this 400-foot stick. When it drops, the only distance it can go is 400 feet. Keep that in mind, okay? This is the ground here. So we've got a ball being dropped from 400 feet. It's falling toward the earth in a straight line. And the distance formula is given by d is equal to 16t squared. So in part A, they want to know at what time did the ball hit the ground, or how many seconds after we release the ball does it hit the ground. Well, if it can only go 400 feet, and this represents the distance, then we say 16t squared is equal to 400. And if we solve for t, we get, all right, t squared is 25, so t is 5, right? We get 5 seconds. It takes 5 seconds for the ball to hit the ground. That's a 5. That's important because, we want to calculate in part B the average velocity. And we know that the average velocity, again, is f of b minus f of a over b minus a. Remember that average velocity and instantaneous rate of change, they mean the same thing, all right? They're just asking you in a different way each time. So anyway, I need my b minus a. Well, what's the interval? At time equals to 0, the ball hasn't been released yet. And at time equals to 0, the ball has hit the ground. So it's taken 5 seconds, so that's my interval. So I'm looking for f of 5 minus f of 0 over 5 minus 0. Well, f of 5, I have to compute it, right? So over to the side, f of 5 is 16 times 5 squared, which is 400. And f of 0, well, that's just 0. So not too difficult to compute. So this is going to be 400 minus 0 over 5. And 400 divided by 5 is 80. And you want to include the units because we're talking about velocity. All right. Let's see, there's A, there's B, and then now there's part C. So again, when a ball hits the ground, it doesn't just fall and stop like a brick. It continues to bounce and bounce and bounce and bounce and bounce, bounce, right? So what you can think of is a number line, and this is the point or the time where the ball hit the ground. So we know just a split second before that, we can call that 4.9, right? And just a split second after that, we can call that 5.1. And we can use those little intervals to compute or to estimate our instantaneous velocity. So, I can do f of 5.1 minus f of 5 over 5.1 minus 5. And I can do f of 5 minus f of 4.9 over 5 minus 4.9. So in this one here, of course, I'm going to have to calculate that, right? So if I come over to the side and I think of f of 5.1, well, that's 16 times 5.1 squared. And f of 5 is 16 times 5 squared, which is, that I know is 400. All right, so this is the one that's a little bit off. Just like this is going to be the one that's a little bit off that I really need to compute. So if I do the 16 times 5.1 squared, I'm going to get 416.16. So I get, for this one here, so I'll go this way. This is 416.16 minus 400 over 0.1. And this one here is 400 minus 384.16 all over 0.1. If I compute this one, clear. We've got 416.16 minus 400, which is 1616 divided by 0.1, which is 161.6. Is this right? 16 squared. Let me just double check something. 16 times 5.1 quantity squared is 416, 16. 16 times 5 is definitely, or 16 times 25 is definitely 400. And 16 times 4.9. I just want to make sure my numbers are right. Is 384.16. Yeah, okay. So here we're going to have 416, 16 minus 400 divided by 0.1 is 161.6. Over here, we're going to have 400 minus 384.16 divided by 0.1, which is 158.4. And now if I add those two up and divide by 2, I'm going to get 160 feet per second. Oh, I'm off the camera. Sorry. Okay, so that was part C. In the table, the next one, number 3, here, number 3. Again, I mentioned this in class. He wanted you to find the average velocity between 1.3 and 1.9, so that's your interval, okay? Part B was the issue because he said, estimate the instantaneous velocity at the end point here, all right? So that's what I had done in class, but this is the point where he was curious about. If you look at the answer key, he's clearly trying to find or estimate the instantaneous velocity at t is equal to 1.5. All right, so just be aware of that, that they're not going to match. And I'll do this one. I did the endpoint in class, but I'll do this one so you can see how it's done. It's done just like the last one. So let's move this out of the way. Let me bring my paper down because there's so much paper. Let me move my camera too. I just have so much stuff going on. Move the light. Make the light a little better. Move this paper this way. Here we go, this way. Oh gosh, it's so annoying. Okay, so in part A of number 3, so this is number 3, part A, we want to find the average velocity on the interval from 1 to 9. Oh, we know that that's f of 9 minus f of 1. Oh, sorry, 1.3. 1.3 to 1.9. So this is equal to f of 1.9 minus f of 1.3 over 1.9 minus 1.3. Okay. If you look at the table, f of 1.9 is 5.3 and f of 1.3 is 5.1. So I'm just going to plug those numbers in. So we have 5.3 minus 5.1 over 0.6. And this is 0.2 over 0.6, which is 1/3. So that was A. Now in B, again, in the answer key, he's finding the estimate of the instantaneous velocity at t is equal to 1.5. So what you want to do is you want to choose a point a little to the right and compute the slope of the secant. Choose a point a little to the left and compute the slope of the secant, and then average the two. All right. So what we have here in part B is we want to estimate the instantaneous velocity at x equals to 1.5. So again, I can do the instantaneous velocity is approximately equal to f of 1.6 minus f of 1.5 over 1.6 minus 1.5. And I can do f of 1.5 minus f of 1.4 over 1.5 minus 1.4. Okay. So if I compute those two average velocities and then average the result or the outcomes of those, then I'm going to get a good estimate of instantaneous velocity. Now, again, kids have mentioned in class, and it's true, that as long as my interval width is equal and my points are close by, then what I could do is actually f of 1.6 minus f of 1.4, because 1.5 is right in between those, over 1.6 minus 1.4, and get the same answer. So f of 1.6 is 5.7, f of 1.4 is 5.2, and 1.6 minus 1.4 is also 0.2. And this is going to be 0.5 over 0.2, which is 5/2, all right, or 2.5. So this would be the answer in the key for that one. Number 4, the average rate of change. So we're going to do number 4. The average rate of change of a function, which we know is this. The average velocity, average rate of change, again, we use them interchangeably depending on the context, on the interval from 1 to 9 is equal to 3, okay? So we also know that f of 1 equals 5, and we want to find f of 9. Okay, so we know that a rock is equal to f of 9 minus f of 1 all over 9 minus 1, and that's equal to 3. So I can leave this piece out of it now, okay, and just focus on solving this little equation. F of 1 we're told is 5, so f of 9 minus 5 over 8 is 3. And what we're going to do is we're going to solve this little equation for f of 9. So we're going to multiply both sides by 8, so f of 9 minus 5 is 24. Adding 5, we get f of 9 is 29, and we're done. Number 5, we have g of x equals x squared plus 5x. First thing they want you to do in A is find the average rate of change on the interval from A to A plus h. So it's just weird, you don't have from, 0 to 5 or something. You have weird little expressions, and that's fine. This is always your A, this is always your B. And if we're looking for average rate of change, we know that that's going to be f of A plus h minus f of A all over A plus h minus A. And those A's are going to cancel, right? So it becomes f of A plus h minus f of A all over h. Well, we have to compute this piece here, what f of A plus h is, or g. I should call these g because this function is g, so I'll change them to g's. So g of A plus h is A plus h quantity squared plus 5 times A plus h, which is just A squared plus 2AH plus h squared plus 5A plus 5h. And I cannot simplify that. So now I'm going to compute g of A, which is nice and easy. It's just A squared plus 5A. Okay. So what we're doing is we're finding the average velocity or average rate of change of the function g at some point x equals to A. We don't know what the point is. So what's going to happen is we're going to get an expression. So now we're going to take, remember, this mass, and we're going to substitute it into this piece of the expression. And then we're going to take this one here, this expression, and substitute it in for g of A. Since you have more than one term here and there's a minus here, make sure you put this in parentheses so you don't forget to distribute. So what we're going to have is that the average rate of change is equal to A squared plus 2AH plus h squared plus 5A plus 5h minus A squared plus 5A all over h. And if I distribute this sign, I'm going to have A squared plus 2AH plus 5A plus 5h minus A squared minus 5A all over h. And at this point here, I can see that the A squares are going to cancel and the 5A's are going to cancel. Now I'm going to factor an h out of the numerator. So we're going to have 2A plus, I'm missing a term. There was a plus h squared in here. I missed a term. Plus h plus 5 all over h. Those cancel. And so we get this expression 2a plus h plus 5. So this is my average rate of change of this function g at the point where x is equal to a. If it were at the point where x is equal to 1, then it'd be, 7 plus h, okay? Now in part b, they're asking you to find the formula for g prime of a. This means what is the derivative of this function at x is equal to a? And we know that the derivative is given by the limit as h approaches 0 of g of a plus h minus g of a all over h. Well, we found this piece. It's right here, right? We found it and we cleaned it up. So this is the limit as h approaches 0 of 2a plus h plus 5. And if I plug my 0 in, if I take my limit, I'm going to end up with 2a plus 5. Okay, so the derivative of a function at a point where x is equal to a. We don't know what a is, which is why we get a new function. Okay, if I knew what a is, I'd plug that a in and we'd get a number, which would represent the slope of the tangent line. So that was number 5. Number 6. So I was going to print a new graph, but I'm not going to. So this is very simple, okay? They just wanted 2 simple graphs, but they're trying to get you to recognize here. They want you, so this one is in purple. Okay, this is the purple graph here, or the lilac graph. But they want you, you need to recognize that this is f of b minus f of a over b minus a. It's the slope of a line between the point, it's the slope of the secant line, between the points 1 and 4, right, over b minus a. B minus a. So this is my a, this is my b. So you go to when x equals to 1 up till you touch the graph and plot a point. Then you go to 4 up till you touch the graph, plot a point, and connect them with a line, and we call it L1. And this one here, what they want here is they want to sketch a line whose slope is this. Well, this is the derivative definition, right? They want us to find or draw the tangent line at the point where x equals to 3. And so that's the pink line. And label it L2. That's all you had to do for that problem. Number 7. Another ball problem, right? So a ball is thrown up. Oop. A ball is thrown up with a velocity of 96 feet per second from a height of 112 feet. The height of the ball for t greater than or equal to 0 is given by this function here. Find the maximum height of the ball, find the average velocity between 0 and 7, find the velocity at t equals to 3, and estimate the velocity at the instant it hits the ground. So it's a pretty involved question. And, all you need is algebra, essentially. So let's have a look. Our function, h of t, is equal to negative 16t squared plus 96t plus 112. Now we know just by, gotta focus. We know just by looking at this function that this is a quadratic function, meaning its graph is a parabola, and it's going to open down because we have negative out here, right? So I know that my function looks something like this, and I know that the top of the mountain is the maximum. And in part A, what we're trying to find is the maximum height of the ball, okay? So remember that with quadratic functions, you can find the x-coordinate of the vertex using the formula x equals negative b over 2a. And if you can find the x-coordinate of the vertex, then you can plug that into your function to get the y-coordinate, which is going to represent the height of the ball. So don't forget that the y-coordinate is always the height of the function at the point where x is equal to whatever x is equal to. So remember, too, that this is a, including the sign, this is b, and the constant's always c. So what we have here is x is equal to negative 96 over 2 times negative 16, and that's going to be 3. So what I know is on my graph, when x is 3, then y is going to be something. The y-coordinate, I can say, is negative 16 times 3 squared is 9, plus 96 times 3 plus 112, which is 256. So the maximum occurs at the point 3, 256, where the y value is the height of the ball. So we'd say the maximum height is 256 feet. Easy peasy. In part B, you want the average velocity on the interval from 0 to 7. Also easy peasy, okay? It's plug and chug. So you have to evaluate h of 0, which is 112. No work there. If I plug the 0 into this function, all of those terms are going away except the last one. And if I plug the 7 in, well, I'm going to have negative 16 times 7 squared is 49, plus 96 times 7, plus 112. And I forgot what that was off the top of my head. So I'm going to recompute it. And it looks like it's 0. Yeah, good. 0. All right. So if I know my average velocity formula is f of 7 minus f of 0 over 7 minus 0. Well, that's going to be 0 minus 112 over 7. And that's 16, negative 16 feet per second. Okay. Again, I needed my calculator to do some, tedious arithmetic, but other than that, not much. Now, we want to find the velocity of the ball at t is equal to 3. Well, again, if you would realize what a quadratic looks like graphically, it's a parabola opening down. And remember the fact that at t equals to 3, that's where your maximum height was. Well, all you have to do is draw a tangent line to t equals to 3, and we see that its slope is 0. So for part C, all I have to say is that the velocity when t is equal to 3 is 0. And better yet, mathematically, you'd say v of 3 is 0. Okay, I don't know what the velocity function is, right? Well, you don't know yet. I know what it is, but you don't know how to find it yet. And that's okay, because it's simple enough. You don't really have to do any work, but you do want to denote it mathematically. So the velocity at time equals to 3 happens to be 0. And then finally, in D, they want you to estimate to the nearest hundredth the velocity of the ball the instant it hits the ground. Well, we haven't discovered the instant that the ball hit the ground yet, and we have to figure that out, all right? So using our function, we have negative 16t squared plus 96t plus 112 equals 0, okay? And I'm going to factor a negative 16 out, and we're going to have t squared minus 6t, watch that sign, okay, minus 7 equals 0. If I divide both sides by negative 16, it's going away, so you can disregard that. So what I want to do is I want to factor this to find time. So this is going to factor down quite nicely to t minus 7 times t plus 1, okay? And, if I solve this factor, I get a negative time, which we can't have, so we get that at t equals to 7, the ball hits the ground. And so now I know when the time that the ball hit the ground. So again, if I think of 7 on a number line, when a ball hits the ground, it keeps bouncing, it doesn't stop. So I could choose 7.1, and I could choose a point a little bit to the left, 6.9, and I could compute those two. So I would say the velocity is approximately equal to f of 7.1 minus f of 6.9 over 7.1 minus 6.9. I'd have to compute h of 7.1, and I'd have to compute h of 6.9 in order to do that. So let's compute it. We have negative 16 times 7.1 quantity squared plus 96 times 7.1 plus 112. And we get negative, so this is negative 12.96. When I compute the second one here, let me copy and paste that. And I'm just going to back enter 6.9 and 6.9. And hit enter, and this is 12.64. So, you know, substituting them into this equation here, I'm going to have negative 12.96 minus 12.64 over 0.2. And if I compute that, I get 128-ish. And that would be negative, by the way. So that's number 7. Number 8, we have this graph here. And you're asked to answer some questions about the graph. So let me try and get that in there better. Okay, in part A, you're asked, when is the car moving the fastest? Again, the car is going to move the fastest when the tangent line is the steepest, okay, in the positive direction. And right about here, we would have the steepest tangent line. Starting right there, they start to decrease. And down here, they begin to increase. So this is about the steepest point, so T sub 2. Is the car speeding up or slowing down from T sub 1 to T sub 2? Well, our graph here is concave up, and our tangent lines, or the slopes of our tangent lines, as we move along here, are getting steeper and steeper. So we're definitely speeding up in part B, okay? And in part C, our graph goes to concave down ever so slightly. And if you think about slopes of little tangent lines, they're pretty steep here, and they become less steep to 0. So we know that the car is slowing down in part C. In part 9, that's a pure calculator problem for you guys. So we have this derivative function. Okay, so they're giving us the derivative, which is x cubed minus 3x plus 1. They want you to sketch it on your calculator and use it to answer the question. So if I hit the graph key, there's my derivative, okay? I have to keep reminding myself that I'm dealing with the graph of the derivative here. And that's not what I want. I want this way. And I want this right below. Okay. I think that fits it pretty good. All right, so in A, it says, what x coordinates on the graph will the tangent lines be horizontal? Remember, this is the graph of the derivative, right? So on the graph of f, f is going to have horizontal tangent lines at the bumps, and those bumps translate as the zeros of the graph of the derivative. So this is my derivative graph. So I've got 1, 2, 3 critical numbers or zeros on this graph, and I have to find them. All right, so let me just zoom out of here so you can see the whole calculator, what I'm doing. To find the zeros, you know, don't just assume that's at -2, 0, and then, ooh, I don't know what that number is. Okay, you need to use the feature of the calculator to get the exact values, because if you estimate it by eyeballing it, you're going to get it wrong and you're going to lose points on the AP exam. So I'm going to start with this 0 here. You're going to do second calc 0, 2. And you're going to right arrow all the way over, just a little to the left of the first 0, and press enter. And then you arrow a little bit to the right and press enter, and you press enter one more time. So that's the point. I'm just going to jot it down over here. This is x equals -1.879. Okay, that's the first one. Now I have to do it again. Second calc 2. I'm going to arrow over to the next 0 I see, a little bit to the left, press enter, a little bit to the right, press enter one more time. And it looks like we've got 0.347. And one more time, second calc 2. All right, we're going to move a little to the left of that 0 and press enter, a little to the right, press enter, enter one more time, and it looks like that's x is 1.532. So those are the 3 x coordinates for which the graph of f would have a horizontal tangent. Okay, they look like the zeros on the graph of the derivative. In part B, suppose you were given f of -1 equals to 5. So I don't need the calculator there anymore. Well, I'll hang on to it because yes, we can use it. So f of -1 equals to 5. They want us to write the equation of a tangent line when the graph is the graph of f at -1. So if I knew what the graph of f was, so let's just pretend for a second that, this is the graph of f. And at x equals -1, I wanted to know what the equation of the tangent line would be at that point. Well, I don't know what the graph of f is, right? But what I do know is that I have this point -1, 5, and I know I need a slope. Every point, I'm going to zoom in on this again. Every point on this graph represents the slope of the tangent line to the graph of f, okay? Now, if you go to second graph key, that's your table. Oh, let me change my window. I'm going to start at -1, and I'm going to go in increments of 1 so it's easier to look at. There we go. So all you have to do is look at your table and go to where x is equal to -1. Well, this is the graph of the derivative, so the slope of the tangent line is 3. The y value means the slope of the tangent line is 3. So I have my slope here. So now I can write my equation. Y minus 5 is equal to 3 times x minus a -1, or y is equal to 3 times x plus 1 plus 5. Done. In number 10, this is purely calculator. Number 10, we have the absolute value function. So again, remember to get the absolute value symbol, you're going to press math right arrow 1, and that'll put those absolute value symbols in there. What we have is x to the 4th minus 16. Okay, so we definitely have this absolute value function, and we're going to hit the graph key. And we've got a couple of sharp corners. Now, there's stuff going on in the middle here that I can't see, and you need to see every aspect of your graph, okay? So when that happens, it means I can't see high enough on the y-axis. So you go to you go to window, okay? And you notice in the x and y direction, I've got a square window, -10 to 10 and -10 to 10. So I just want to go on the y-axis here and move it up to like 20, right? And hit the graph key again. And so now I can see up higher on the y-axis, and I can see my graph, which is important. So in part A, it says, what can you say about g prime of 4? Well, again, this is pretty steep. I would have probably said that it's undefined or that it doesn't exist. However, right, if you do second, oh, wait, you can't see the calculator here. Sorry, it's going backwards. If you do, so second draw, which is the program key, and then number 5, second draw, you see 5 is tangent line 5. And then you have to tell your calculator, at which point do you want to draw the tangent line? Well, we want to draw it at x equals to 4, right? And you do that, you're going to get 200 and something. I forgot what the number was, 256, okay? So you'd say g prime of 4 is 256, okay? And it says, all right, what about at g prime of 2? Well, at g prime of 2, the derivative is not going to exist there, okay? It can't exist there because of the cusp. And at g prime of 0, no work done there. If I go to where x is equal to 0 and I draw a tangent line, it's horizontal, okay? The other thing is you could do second draw 5 at 0, and it's going to draw that horizontal tangent line for you, and it's clearly 0, okay? So really easy to do with your calculator. Now, in the second part, they've got this 4th root. So again, to put some weird root index, okay? So, the little number here is, this here number is called the index, all right? And this is the 4th root. You need to press the index first and then math, and you scroll down to the x root, Okay, and then that will set you up into your fourth root. And then we have x minus 1 quantity at, not apps, x minus 1 quantity to the fourth, and plus 0.1234516. Okay, 5 zeros and a 16. And I'm going to graph this. And they were trying to trick you in this problem, if you recall from class. That definitely looks like a sharp corner at x is equal to 1. And they want you to find all values of x for which the derivative does not exist. So as a kid, I would look at this and say, oh, at x equals to 1, the derivative doesn't exist because there's a cusp there, right? But if you recall, upon further inspection, so always look at the cusps. Now, I didn't do the last one I just put in, this graph, because I had already inspected that, no matter how much we zoom in on this, it's going to stay a sharp corner. But here, if I do trace 1, enter, it puts my cursor on that value on the graph. And now if I do zoom 2, I'm going to zoom in. All right, so the first zoom, I believe it still looks like a pretty sharp corner there, and it does. And if I hit enter again, it's going to zoom in again. And as we get zooming closer and closer, it becomes very clear, and I'm going to move my cursor because I think it's going to be in the way. It becomes very clear that that's rounded. So depending on the window, it looks like a really sharp corner. But if you inspect it or investigate it, you see it's not a sharp corner. So we would say that the derivative exists for all values of x. And you can say f prime of x exists for all x. So that big upside down A here, capital A, that means for all in math. Okay, you're done. You don't have to write that, but if you did, the graders would understand. And they'd say, ooh, a sophisticated kid. All right, next one. Let me move these out of the way and get to a clean sheet of paper. So the next one says f of 2 is equal to 3, and f prime of 2 is equal to 4. We want to find the equation of a tangent line. So we want to find the equation of a tangent line at x equals 2. No big deal. We have a point. The point is 2, 3. We have the slope of the tangent line, which is 4. So we know that the equation is just going to be y minus 3 is equal to 4 times x minus 2, or y is equal to 4 quantity x minus 2 plus 3. Done. In part B, they get a little bit of a twist on the same question. It says if f of x is equal to x squared and f prime of x, so they're telling you what the derivative function is, they want you to find the equation of a tangent line at x equals to 3. Well, now I don't have a point and I don't have a numerical slope, but since I know where I want to find this derivative, I can plug it in. So f of 3 is 9. Voila, I have the point 39. And the derivative at 3 is just 2 times 3, which is 6. So I have a slope. Okay, and so I'm going to have y minus 9 is 6 times x minus 3, and you can rewrite it in its proper form. Part C, f of x is equal to 2e to the 3x, complex function, okay? You don't know what the derivative is, but you want to find the equation at x equals to 0. Well, that's when you take out your calculator, okay? And you put that function into y equals. So it's 2e to the 3x. You hit the graph key. Oh, I got to change my window. So I'm going to do a zoom 6. Zoom 6, zoom 4 is a standard window. There it is. And at that point, I can do second, draw 5 at x is equal to 0. Oops. Second, you see how I press buttons and they don't press? Second, draw 5 at x equals to 0. And not only will that draw my tangent line, it's going to give me the equation. And it's clear that we got the line. We would say y is equal to 6x plus 2. Done. It tells you use n deriv. You know, you could have found the slope by using n deriv. I think this is easier, but you know, whatever floats your boat, whatever makes you happy. Okay, number 12 is where we get to the graphs. So I didn't get this far in the first video. Turn. Okay, so this is the graph of f, all right? And we're going to answer some questions. Where is f prime positive? We know that f prime is positive when the graph of f is increasing, right? And this occurs from -2 to 2. Done. That's A. B, where is the second derivative positive? The second derivative is positively valued when the graph of f is concave up. And where does that occur? Well, f appears to be concave up from -5 to about 0. Done. C, what are the critical numbers of f? In other words, where are the bumps on the graph, the x coordinates on this graph? Well, we'd say at x is equal to -2 and 2. This is the graph of the derivative, so I have to be very careful. Where is f increasing? F is increasing when f prime is positively valued. F prime is positive from -4 to -1 and from 3 to 4. B, where is f concave up? Well, f is concave up. Now remember, I'm using shorthand notation to save time. F is concave up when f prime is increasing. Well, f prime is increasing from -4 to -3. It's also increasing from about 1 to 4. Okay, the tricky one. If f of 1 is 0, so again, we're talking about f of 1. If f of 1 is 0, here's my function f. It's got to go through this 0, right? Either this way or this way somehow. Is f of 0, so is f of 0 somewhere along here? Is f of 0 positive or negative? In other words, is it above or below the x-axis? Well, think about this. F prime is negatively valued from -1 to 3. All right, so here's my reasoning. F prime is negatively valued on the interval from -1 to 3. That implies that the graph of f has to be decreasing on that interval. Make sense? So if f is decreasing and it's got to go through the 0, it's got to be above the x-axis at x is equal to 0. Does that make sense? I hope it does. Done. Okay, next one, 14. We have to answer some questions, right? So we want to list all the label points for which the derivative is positive. The derivative is positive when f is increasing. F is increasing from A to C and from E to H. And again, we're not including the endpoints when something's increasing or changing concavity. So it would be point B. And then on this one, on this interval, would be F and G. The critical points of F, those are the bumps on the graph of F, right? That would be C, E, and H. And then in part C, they want us to label all the points for which the second derivative is positive. The second derivative is positive when the graph is concave up. The graph appears to be concave up from about D to F-ish, like right around here. So I would include the point in the middle, and I would say point E. Also, I almost forgot. Over here, these critical points, A is an endpoint and K is an endpoint. So those would also be critical points, right? Meaning that the derivative is not going to exist there. 15, forget. You're not going to be tested on that. Number 16, total calculator, right? You're given a position function. Again, it's going to take a minute. It's going to be a little annoying. But what you're going to do is you're going to put that position function into your calculator. So it was t to the 4th minus 2x squared minus 6x. You're going to put the function in. Move this down. And then remember, we're going to use our math 8 to get the derivatives. And I don't care about the graphs. Okay, the graphs are too like crazy for me. But anyway, let's do this. Down here, we're going to press math 8. We always put an X in the first box. Vars, right arrow, 1, 1. Tells me take the derivative of the function sitting in y1, always with respect to x or over the entire domain. Go to y3 and do math 8. X, vars, right arrow, 1, 2. So I got to be careful here. I want the first derivative of the function sitting in y2. So I need to input that. And again, over the entire domain. I'm going to hit graph, and we're going to have to wait a couple minutes. And you're going to have to wait until all those graphs come up, because it's not going to generate the table until you can see the graphs. And as we saw in class, it takes forever. It was the second derivative that took forever. Oh, yeah. And still not up yet. And here we go. Finally. So I'm going to wait another few seconds, because if I try to, it's still graphing. And how I know is that my little wheel is still spinning. And I get impatient. I try anyway, but it never works. So patience is a virtue. Okay, the wheel's gone. So now I'm going to go like this. I'm going to go like that. There we go. Okay, and remember that the first function in y1 was the position function. Y2 was the first derivative, and y sub 3 was the second derivative. So at the values in question, which are namely 0, 1, and 2 from the table here, let's move this way. 0, 1, and 2. Where's my calculator? Over here. This is good. You know, to fill in the table, so when x is equal to 0, you can just scroll down. I got 0, -6, -4. Sorry, wrong. That's wrong. When x is 0, my first derivative is 0. My position function is 0. My first derivative is -6. And my second derivative is -4. When x is 1, my position is -7. My first derivative is -6. And my second derivative is 8. And when x is equal to 2, my position is -4. My first derivative is 18. And my second derivative is 44. Table filled. Okay? And then in part B, they wanted to know, is the speed increasing? Well, what you want to do is look at, and that was at t equals to 1. What you want to look at is the signs for velocity and acceleration. And if they're different, negative, positive, positive, negative, whichever way they go, if they're different, then the speed is decreasing. 4 more problems. Limits, number 17. This way. Let me zoom in a little bit more. Let me bring this down and this way. Gosh, it's so like sickening to the eye. So I'm going to clear out my y equals, because you're going to want to see the graphs of these limits, all right? And I'm going to show you how I put them into the calculator. So for the first one, everything in the numerator needs to be in parentheses. X squared plus x. Close the parentheses. Divided by, and then parentheses, square root of 4x squared plus x cubed. Okay, go outside of the box, close the parentheses, hit the graph key. We clearly have a break in this graph here, so we know the limit from the left does not equal the limit on the right, so we would say the limit does not exist. second one. Okay, I'm going to go in here, clear this out. Whole numerator in parentheses. So parenthesis, 1 minus parenthesis 1 divided by x, close the inner parenthesis, and then parenthesis again, divided by quantity 1 minus x, close the parentheses, hit the graph key. We're looking for the limit as x is approaching 1. Okay, so don't be confused by this break at 0, because that's where your eye is going to go. That's how they try to trick you. They're looking for the limit as x approaches 1 from the left and the right. And it is some number. It exists, right? So remember, if I go to my table now, I don't see, at x is equal to 1. Oh, it's saying x is equal to 1. There's an error. Is that for real? Actually, I didn't see that in class. Let me trace 1 and zoom in on that. Let me look at the table again. Still saying error. That's interesting. But it's okay. I don't see a hole there. There shouldn't be. Well, there's a removable. I think it's a removable discontinuity. So even if there's a hole, the limit's still going to exist. So remember, what I've got to do is I've got to reset my table. So you go second window. Now you go to this window key. Now you always want to start your table where the limit's being taken. So the limit's being taken at 1 here. So I'm going to change this to a 1. You just press the number and enter. And it'll bring you down to table change. Okay, I don't want it in increments of 1 because I'm never going to see what the limit's approaching. So normally we just put 0.001. You can use that all the time. It's the best thing to use. And from here, do second table, go to your table. And now you're at 1, right, where that limit's being taken. And there's definitely an error. But if you come in from the left, you're approaching -1. And if you come in from the right, you're approaching -1. So you'd say that the limit is -1. In the third one, you could plug the 2 in. So you get 2 squared minus 3 times 2 plus 7 over 2 squared minus 9. No problems here. It's 4 minus 6 plus 7 over 4 minus 9. That's going to be 5 over -5, which is -1. And this one here, you're definitely going to have to use your calculator for something like that. So again, in the numerator, you've got the sine of 2x. Again, remember your calculator must be in radian mode, divided by 3x, close the parentheses, hit the graph key, and you can not see the hole there. There's a hole, okay? If you look at your table, now remember, we want the limit as x goes to 0. I'm going to have to scroll an awful long way to find 0 on this, right, with the way it's set. So you go back to table set. You start at where you want your limit to be taken, 0.001, and now go to your table. And there's the error at 0. And as you come in from the left, the height is 2/3. And as you come in from the right, the height is 2/3. And so you'd say the limit is 2/3. In number 18, we've got a very disjoint graph, okay? And so 18 is all about continuity. At what x is g not continuous? Well, they're not asking for a reason. So we'd say -4, -2, 0, 1, and 3. He might have included 4. Yeah, we'd include 4. Okay? Not continuous, because this up here I didn't catch. There's a definition there. All right, done. What's the limit as x approaches -2? If we come in from the left, it's -1. If we come in from the right, it's -1. So it's -1. C says, what is the slope of the tangent line to this graph at x is equal to -1? If I go over to -1 and I draw a point and a tangent line on that, it's going to have the same slope as this function. I'm eyeballing it and saying it's -1, and I'm done. What's the limit as x approaches 3 from the left? If we come in to approach 3 from the left, the limit is 0, and this you didn't have to do. the piecewise function. Is it continuous at 3? No, it's not, because we have a removable discontinuity, all right? Again, if I plug a 3 in here, I'm going to have division by 0. I know if I factor the top, then I can remove that discontinuity, but we're not being asked to do that. We just want to know, is it continuous? And we would say no, because there exists a removable discontinuity, okay? So no. F prime of 0. Well, I need to graph this. So again, let's look at how to graph a piecewise function. I'll zoom out so you can see the calculator better. Turn it on, and let me get out of here. So remember, we're going to enter the piecewise function in this way, in pieces, okay? Pieces this way, okay. So the first piece is this, all right? And I need to put it in just as I see it. Don't factor it or anything like that. So I need an outermost parentheses and all this stuff in the numerator, and then denominator has to go in. So it's going to be x squared plus x minus 12. Close the numerator, divided by parentheses x minus 3. Now, close it all the way, and then I need a new parenthesis to put the restriction in. So parenthesis, and then math, parenthesis, and then second math does not equal. So 2, I forgot to put my x, hang on, x cannot equal 3. Close the parenthesis, okay? To put in the next piece, I have to press plus. Now, since I just have the number 0, I can do 0. I don't need a parenthesis. Times parenthesis, x second math equals, which is 1, 3. Close the parenthesis. Hit the graph key. Oh, I put something in wrong here. Okay, so it's telling me, forgot my outermost parenthesis. See, parentheses. Okay, hit graph. And I'm going to probably have to fix my window. So zoom 6. Here we go. And again, this looks like a function without any problems at all. However, if I inspect this thing at 0, okay, if I want to know the limit at 0, I want to go to my table, and at 0, the limit is 4. The height is 4. Okay, so the derivative as x equals to 0 is 4. It's the height of the function. If I come in from the left and the right, I get the same number. Sorry, no, they want the slope of the tangent line. My bad. I'm sorry. Oops. Slope of the tangent line. So again, if I draw a tangent line there, I could do that. I could do second draw 5 at x equals to 0 and draw the tangent line, which is going to go right over the top of that. And I see that it's 1. So the slope is 1. And then if I want the derivative at 3, well, it's not going to exist. If we have a discontinuity of any kind, we can't have a derivative. So you just say it does not exist. And finally, number 20, the last one. We have a function, the second derivative of a function in this graph here, and we've got to answer some questions. So it says, on what intervals is the graph of f concave down? We know that f is concave down when the second derivative is negatively valued. The second derivative is negatively valued from -3 to -2. And that's it. Done. Where on the graph of f will there be points of inflection? Points of inflection occur when the second derivative equals 0 and changes sign. Well, I see 2 zeros on the graph of the second derivative. I see this 0 right here, and I see this one here. But here it doesn't change sign, okay? Here it does, so I would say at x is equal to -2. I would expect on the graph of f to see a change in concavity at x equals to -2. Now, in C, if f is decreasing at x is equal to -2.5, so I think this is messed up. I think what he meant was f prime here. Just skip this one because I looked at his answer key, and he's talking about f prime in there. This says if f is decreasing at x equals to negative 2.5. Is f increasing or decreasing? Well, if f is decreasing, it can't be increasing or decreasing. So there's clearly an error in this part, so forget about it. That one has been driving me nuts, and that's why. It's because I think he made a mistake and he meant if f prime is decreasing, is f increasing or decreasing? So forget about it. And that's your chapter 2 review, and I hope this helps.